Welcome to Chapter 8, Part 1, Lewis Symbols and Octet. So Lewis dot symbols. So an American scientist, G.N. Lewis, developed a method for drawing valence electrons. And so G.N. Lewis wants to develop a method because the valence electrons are responsible for bonding. So valence electrons, I like to abbreviate that VE, are responsible for bonding. And so in this section of the course, we're really going to start to think about how do we make a molecule. So if we were to think about sulfur, sulfur is element 16. And so when we think about that, we can think about the electron configuration, which is 1s2, 2s2, 2p6, 3s2, 3p4. So when we do this, we know that these are the core electrons. And these 6 out here are the valence electrons. So when we think about the valence electrons, we only want to account for the exterior electrons. So we could have rewritten that as the neon core with the 3s2, 3p4. So in this section, we're going to start to draw something called Lewis dot structures. Lewis dot structures give electrons a place around an element. So for sulfur, we are going to think about where they go. So if you've heard about the Octet Rule, this is the development of that. So for valence electrons, there are 8 valence electrons for any given object. You can put 1 on either side, and then they fill around. And so in this case, they do want to be symmetric. So valence electrons tell us where the electrons are. Now we know that they're in the 3s2 and the 3p4. If you have taken a different chemistry course and you know that these electrons are not really in a Lewis dot structure, that's okay. We are building up to the VSEPR theory where we can see them in 3D. So in the next several moments, we want to think about what does it actually mean and where are the electrons. So the best thing to do is really to draw a bunch of examples. So let's think about boron, nitrogen, neon. And then we'll do a few more after this. So when we think about boron, the number of valence electrons is 3. So we can look at the periodic table and count that across. And so when we draw our Lewis dot structure, we get electrons on 3 out of the 4 sides. We lost that one. So when we think about nitrogen, nitrogen is going to have 5 valence electrons. And so we'll add those 1 on all 4 sides. And then we have the last one. So this last electron could go at any of the positions to where we have 1 pair and 3 single electrons. Neon has 8 valence electrons. And so when we add these, we get 1 on either side. And then we can refill. You'll notice that I fill in a pattern. So for neon, all 8 sites are filled. And so we could continue this with aluminum, which is just under boron. It has the same number of valence electrons, a different core. So if we look at boron and aluminum, there are 3 valence electrons. Now I drew them in 2 different shapes, but that's okay because it's just 2 across from each other and 1 on the other side. So if you drew one for magnesium with 2 valence electrons, in my course, I want them to be across from one another. So this is how we fill those. And so we can look at carbon, which has 4 valence electrons, and they are 1 on any side. Make sure when you draw these, you draw them big enough that they can be seen when this is graded. So the octet rule. So we tend to think about the octet rule, and we've thought about it and we've heard about it, where the octet rule states that atoms tend to gain or lose electrons to form octet. Now, I mentioned that there are 8 seats at the Lewis dot table. And so when we think about chlorine, which has 7 valence electrons, we could draw the valence structure as one like this, or the Lewis dot structure, sorry. It's where we have our 7 electrons. We know that preferentially when chlorine becomes the chloride ion, it becomes Cl-, which now has 8 valence electrons. So chlorine wants to achieve octet by adding another electron. And once you add it, they're all the same, but we can see that chlorine minus has octet, which means that it is surrounded by 8 electrons. It also means that it looks like a noble gas. So we know that the noble gas has a full octet. And so on the previous slide, we looked at neon, which has 8 electrons. So chlorine minus has the same structure for the octet. And so in this case, both argon and chlorine minus have the same valence electron structure. So the octet rule is a really good rule. So let's draw a few Lewis dot structure examples for these 5 elements. So phosphorus has 5 valence electrons. So we know that we're going to put the element symbol 1, 2, 3, 4, and we're going to add that last one. I put it at the top. You could have put it anywhere. So you could have also drawn this, oops, we already did that one, or that. The pair of electrons could go on any of the 5 sides, or the 4 sides. What is not an acceptable structure, so I will draw this in red so that we can look back and see, would be to draw the phosphorus and put this structure to where they are unequally distributed. So valence electrons need to be distributed evenly and symmetrically. So chlorine has 7 valence electrons. And so 1, 2, 3, 4, 5, 6, 7. Again, you could put the lone electron on any side. So boron has 3 valence electrons. 1, 2, 3. And magnesium, has 2 valence electrons. So one thing you'll notice is even if we repeated the elements at different points in the video, there are only 8 Lewis dot structures for an element. There are only 8. The question is, what do they look like? So if we have any element, so we're just going to put element E for just element. So there are 1, 2, 3, 4, 5, 6. Whoa, that's not where that goes. 6, 7, 8. Those are the only structures. So you could have taken snapshots as I added each one. Regardless of the electrons, this is where they are. The other thing to note is when we look at the periodic table, we're going to ignore the transition elements because they don't really have valence electrons the way that we think about it. But the number of valence electrons is 1, 2, 3, 4, 5, 6, 7, 8. Where this out here are the noble gases. And here we have elements like lithium, beryllium, and then across as you go. So you can determine the number of valence electrons easily from the periodic table.